Hello class, today we are going to discuss a topic on radar signal processing. Radar signal processing is one of the biggest application of this microwave signals. As we all know that we have studied about the microwave signals yet, and when we talk about microwave signals, we know that radar was a basic cause for the invention of microwave signals. And this radar is the biggest application of this microwave signals. Now, what is the reason behind it? Why microwave is the biggest application, or why radar is the biggest application of microwaves? Radar is the biggest application of microwaves because radars use a very high frequency signals, and microwaves too possess a very high frequency signal, which is applicable for these microwave signals quite oftenly. So, let's start with this topic now. Firstly, we'll discuss about what is radar. Radar is basically radio detection and ranging, and it is basically used for the detection and range to find out detect and range the targets. Because we all know that radio detection and ranging is one of the biggest application of this microwave signals. So, in this diagram, we can easily visualize that we are using a transmitting antenna, by which we are transmitting energy towards a target, and it is being received by the target and it's coming back. The echo signal is coming back towards the transmitting antenna. Is known as backscatter signals. So let's see it elaborately in the next slide. Radio detection and ranging. We have this transmitting antennas. This is the transmitting antenna which is used for transmission of radio signals. These are being transmitted by a transmitting pulse, transmitting towards the target. The target is being perceiving this target and is reflecting back the echo signal back towards the transmitting antenna. So this is one of the basic block diagram of the radar system. So what are various observations which are being used or which are being observed when we perceive such kind of radar system? First is we are using a target range, the target angles. The target angles are azimuth and elevation. The target size, radar cross section. What's the size of this radar? And target speed, that's Doppler. We'll discuss about all of these parameters one by one in this slide only, in this presentation only. So let's have a brief review previously at what is this target range. Target range is the basic range that is from the transmitting end towards the target. What is the range of this target from the transmitting side? Target angles means azimuth and elevation. Now azimuth is the horizontal angle and elevation is the vertical angle. So these are the two angles or the positions of the target from the base station or the radar station. The target size. What is the size of the target? Because that size matters. Radar cross section. What is the cross section of the target? Is that applicable, or is that covering the signal? The signal is being transmitted by the radar station. Is it being covered by that the target size or not? Is it applicable, or is it exactly applicable over that target cross section or not? So that is very important. The target speed, that's the Doppler speed. This we're going to discuss in the next slide. So we'll talk about radar signal processing first. What is radar signal processing? It's a distance measurement, the transient time. Transient time is a time that is taken by the signal from the transmitting end towards the receiving end or the target side and back, the reflected signal back from the receiving end towards the transmitting side. So that is a to and fro motion of the signal from the transmitter towards the target and target towards the transmitter back, and that back signal is known as your echo signal. Secondly, we use the frequency modulation technique for the measurement of distance also. We have the speed measurement categories, we have reduction of interference effects, and we have plot and track detection. So we'll discuss all these parameters one by one in this coming slides. So firstly, we discuss transient time. Transient time, as I have already told you, round trip time for the radar pulse to get towards the target and back towards the transmitting side. That is your transient time. The distance is proportional to time. The time taken is exactly or directly proportional to the distance. If the distance is more, the time taken is more. If the distance is less, the time taken will also be less. That means it's directly proportional to the distance. The distance is 1/2 the product of the round trip time and the speed of a signal. This is very important now. Now the distance that is taken from the transient time is 1/2 the product of the round trip. But when we have to talk about a round trip means from transmitter towards the, yes, round trip from the transmit side towards the target and back from target towards the transmitter. When we talk about this round trip, then at that moment of time, the time taken will be half. Okay, the distance is 1/2 the part of that round trip. So next is radar range measurement. Radar range measurement is this is the exactly the quite a clear diagrammatic representation of radar range measurement. We have this. This is your radar station, transmitting station, from which we are transmitting a transmitting pulse. This pulse is being transmitted from this radar station towards the target, and the target is back reflecting it towards the radar station's reflected pulse. Transmitted pulse, reflected pulse. That is the whole. This is your total range. This is the total range of that target from the transmitter side towards the target side, and this is your reflected range, reflected pulse. The target range is given by CT by C torque by 2, where C is the speed of light and torque is the round trip time. Now next is the frequency modulation. Now modulation, I think we are all clear about the modulation process. Modulation is the suppression of the high frequency signal over the baseband signal. Now this is another form of distance measuring radar. It is a frequency comparison between the two signals, considerably more accurate even with old electronics. It's a frequency comparison. Here we compare the two frequencies from the transmitting side and from the target side. By measuring frequency of return signal, comparing that with the original signal, difference can be easily measured. In this process, when we talk about the frequency modulation radars, we compare the two frequencies. Now the two frequencies are, one is from the transmitter side, the frequency by which the signal is being transmitted from the radar station towards the target, and other frequency is from the echo side or the reflected signal side, which is from the target towards the transmitter side. Now those two frequencies are exactly compared with each other, and that comparison lead to the exact measurement of the distance and range of the target. Next is speed measurement. Speed measurement is change in distance to an object with respect to time. Now what is the amount of distance that is being measured or that is being varied with respect to the object and the time? Because as we all know, the targets are not always stationary, they are moving too. So when the moving targets are taken into consideration, then at that moment of time we have the speed as a limit. The speed is a product of it is a ratio of the distance over time. When the distance is changing in that moment of time, the time is also changing with respect to the distance. As we have discussed in the previous slides, that distance is directly proportional to the time. When the distance will be changing, the time will also be changing. So thus existing system for measuring distance combined with the memory capacity to see where the target last was is enough to measure speed. That is much clear about all this effect. Now the next major effect or the major the role is the interference effects, because we need to know that the interference effects are very much popular in case of radars too. So how can we minimize them? Because interference leads to a deterioration of signals, and that is not required in radars. So we can easily reduce it by using the interference reducing effects, that is by using signal processing. Signal processing is very applicable and very useful when we talk about the reduction of interference signals. So it is used in MTI radars. MTI means moving target indicator radars. These are quite often used in them and other radars too. Now the major or the most important effect is the Doppler effect. The Doppler effect is a frequency shift that results from the relative motion between a frequency source and a listener. It is a frequency shift that results from relative motion between a frequency source and a listener. Means when we are talking, we have two frequencies. When the frequency is being sent from the source and towards the listener side, the relative motion is the frequency shift that is being shifting. The frequency is being shifted from the source and the listener side. That is your Doppler effect, and is directly proportional to speed. Now, next is a block diagram representation of radar signal processing. Here we have the phase detector, which is used for detection of the phase. That is there any phase difference between the previous and the new sweeps? We have the moving target indicator radar, which is used for the measurement of the moving targets. Detector will detect the targets. Plot detector will plot the exact plotting graphs of the signals. We have the plot processor, we have the plot combiners, we have the sensor tracker, multiple sensor trackers. So this is the basic block diagram representation for the radar signal processors, which will be applicable and will be used in the moving target indicator basically. And this MTA radar will be discussing in my next presentation. MTA is one of the most important radar, which is basically used for detection of the targets, and not only simple targets, is used for detection of the moving targets. So this complete representation, we talk about this complete representation, is used for the MTA radars only. So first block diagram is the I and Q phase detector, means when we go to change the phases, if the phases are changed or not. If the phases are being changed, that means the targets are moving, they're not stationary targets. It's given to MTA radar. MTA radar will detect the targets. It will plot. It will give a brief plot about those targets, and then the plot processor will have the complete processing of that plots. Azimuth data, time, plot combiner, and then we have the complete set of the signals, which will give us the range and distance of the targets from the radar station. The signal processor is that part of the system which separates target from the clutter on the basis of Doppler content and amplitude characteristics. So that signal processor is one of the most important part, which separates from the clutter, because clutters are something which are stationary targets, which are not targets basically, but they are presumed or they are assumed to be the targets, and that gives a false representation of the target. That is very much undesirable. So in modern radar system, the conversion of radar signals to digital form is typically accomplished after IF amplification. Now this IF is intermediate frequency, which is being used in the MTA radars, which give the two different sets of frequencies, and the difference are accomplished for the calculation of the exact range of a target. And that actually removes the clutters too, because that moving targets will only be detected and the stationary one will be assumed as the clutters. Clutters are basically the unwanted targets, which are not targets basically, but they are assumed, falsely assumed as targets. These are the various applications of radars, military applications, as we are talking about radars, sonars, and aircraft. Navigational aids, yes, there are altimeters to calculate the height. Air traffic control, to find out when we're talking about aeroplanes or jet planes, we need to know the air traffic. What is the air traffic? So that there should be no crashing of the planes. Law enforcement and highway safety. That is also one major application of this radar systems. So this is all about my presentation today. I hope my session of this presentation will be very helpful for you. If you have any queries, any doubts, your doubts are almost everywhere welcome in my lectures. And if you find anything questionable, you can ask me, you can drop a message, or you can call me up. Okay class, thank you so much for patient listening.